This episode is brought to you by Brilliant, the online learning platform that allows you to learn about interesting and important topics through a fun and interactive method of teaching that enables anyone to master almost any topic. Brilliant helps you build your critical thinking skills, that's what we do here at Skeptic, through problem solving, not memorizing. The Brilliant lessons are active, interactive, in fact. The way it works is you queue up the lesson and you just start playing along. It's big fun. And then they give you little quizzes. And if you get it right, they go, yay, and you move on, you continue. If you get it wrong, they go, try again. And so you try again, explains why you were wrong. And then when you get it right, explains why you were right. It's great. I've been doing a bunch of the lessons at Brilliant. And I find them most useful, including one that I just got a new one queued today. They send you little notices that there's new courses, lessons. This one's under probability theory, which I love. And this is a case study on going viral on X. Why do some posts go viral on X and others don't? Most of mine don't, but some do. And so why is that? And you could put those calculations into a model, which is what this lesson does here, and then make predictions about which posts are likely to go viral and which are not. So go to brilliant.org/skeptic, or just scan the QR code right there on the screen or in the description below. You'll see the link to brilliant.org/skeptic. You'll get a 30-day free trial and 20% off the annual premium subscription. Check it out, Skeptic, brilliant.org/skeptic. All right. So to what extent are the current revolutions, since this is what your new book is about, in large language models and ChatGPT, artificial intelligence, artificial general intelligence, if we get there, is this really the pathway to understanding how the mind works, or is this something different?
Well, you know, that's an interesting question. I think it is very different for the following reason, is that what ChatGPT has revealed is the inadequacy of the concepts and the words that we have for understanding brain function. And words like intelligence, right? Or understanding. You might think that, well, we understand understanding. Well, why is it that experts have such disparate views of whether ChatGPT understands language or is intelligent? Well, the reason is that those words, we're using them in a way that reveals that they're not really strong scientifically defined concepts. In other words, we don't have a real way of testing whether something is intelligent or not. I mean, we have a lot of different ways. I mean, there's just a lot of IQ tests. You know, people talk about solving problems and so forth. But the reality is that, you know, if you can't decide, you know, with any, you know, agreement on a particular test, you're never going to agree on it. So we have to go beyond the words and the concepts, and we have to build a whole new set of concepts now in the 21st century based on a lot more that we now understand about brains and also about computation, and especially these new large language models. The generative class of models is really phenomenal, that we really don't understand how they work, but there's nothing stopping us from understanding. And once we understanding, we'll have a much better way of going back into the human, and not just humans, but other animals, and understanding how their intelligence evolves and how it emerges from different brains.
Yeah, how we use those words and what we mean by those words, like he remembered or she figured it out or thought. I'm going to read you a passage here. I quoted my own professor, Douglas Navrick, who I got my first degree in experimental psychology at Cal State Fullerton. He studied under Douglas Fantino at UC San Diego, who got his PhD under Herrnstein at Harvard, who worked with Skinner. So that's my four-step removal, my Kevin Bacon number.
Right.
So here was his complaint about that. He was a behaviorist. I reject mentalistic explanations of behavior. For example, attributing behavior to theoretical constructs that refer to internal states like understands, feels that, knows, gets it, figures out, wants, needs, believes, thinks, expects, pleasure, desire, etc. The reified concepts that students routinely use in their papers, despite instructions that they can lose points for doing so. Because what do we mean by those words? We throw them out. So your point is that, we need to operationally define exactly what you mean by those words and then build models.
Well, okay, so no, I want to throw out the words, all
Okay.
the words. I think that the language and words is a very poor way for describing things scientifically, unless you have very, very, like you say, operational definitions, like for mass and energy, for example, in physics, right? If you could make measurements and everybody agrees on the measurement, then you can make progress. No, I think that what really is going to happen, and it's already beginning to happen, and it's happening on a massive global scale, is that we need mathematical understanding. In other words, we need to be able to analyze, for example, ChatGPT, understand how the architecture, the self-attention, how it is trained and so forth. These are just functions, and mathematicians can analyze functions, right? That's what they're good at, and so eventually we'll have a real theory for how ChatGPT works. And I think that once we have that theory, we'll have a better crack at understanding how our own brain works. It's a much more highly evolved and obviously more complex system, but it may be that there are some general principles that will be able to emerge from the mathematics that will give us a really strong intuition, not just language and intuition, but a quantitative theory in the same way we have quantitative theories in physics, but maybe in a very much more sophisticated way, and very okay. Now here's the real difference. Okay, mathematically. So I gave a talk. It was the closing talk of a National Academy meeting in 2017 on the science of deep learning, and this is still early days, right? We're talking about 7 years ago, right? And deep learning kind of took off 10 years ago, so it was like 3 years in, and where were we? I mean, basically, this is very early days, right? I mean, and so who actually was responsible for deep learning? It wasn't the mathematicians. Now they're trying to play catch up, right? They organized the meeting. It wasn't physicists. It was engineers. Engineers built it, from trial and error. The same way that the steam engine was first put together by James Watt. By the way, steam engine wasn't very efficient back then. In fact, it blew up every once in a while. Why? Because he didn't know how to regulate it, the temperature, right? I mean, you'd have to come up with some way to make sure it doesn't get too hot. And the problem is that the steam, expands, and it was a difficult problem. But it wasn't until much later the physicists came along and created thermodynamics, right, which can help you understand the trade-offs and also help you optimize. And so now we make a much better, safer steam engine. It took 100 years.
Right. So the whole physics of thermodynamics, including the famous laws of thermodynamics, really are derived from the original actual engineering problem of designing a steam engine. Yeah.
And you go through history and you'll find that the kernel, the first working systems were always done ad hoc by engineers who had intuitions about how to put things together to get things to work and so forth. And eventually, it emerged how to improve, and not just improve, but to understand. Okay, this in physics version. Here's another good example. Notre Dame. So Notre Dame was built over 1600, over a period of 200 years, 200 years. And they just didn't build it once. They built it many times because it kept falling down. You build these incredible walls and vaults and things and so forth. And the flying buttresses, by the way, they're up there to help support the walls. They're not that, it's not an architectural beauty. It's very practical, and it managed to, they managed to, at the end, figure out how to do the joists and things, and that was all trial and error over many, many, many generations, right? And so that's engineering. That's how engineers created amazing things. Or the pyramids. We still don't know how the pyramids were created, but it's still going on. We now really owe the engineers an enormous debt for being trailblazers and just creating things that work. Sometimes they don't. Like unfortunately, the Boeing Max, right? You know.
Well, complex systems, maybe.
Yeah, that's right. That's right. No,
and
but
also in the airline industry, it's a zero tolerance. We can't have any errors.
That's right. No, in fact, I actually know I'm collaborating with a control theorist who actually was responsible for something called H infinity. John Doyle at Caltech.
Yeah. Okay.
Yeah. So John.
What is that? H infinity.
Oh, H infinity. Okay. So here's the thing: is that if you do traditional control theory, is you want it to work on average. Okay, that's not good enough. If worst case is a disaster, right? You can really think can really get a very you lose an airplane, you lose a couple hundred people, right? You don't want that. So what he did was to modify the theory to be more robust. So it's a form of robust control theory that guarantees that in the worst possible case you don't crash. And it's funny because he lived through that period. By the way, he was working for an aerospace firm at the time, Honeywell, I think it was, and they were building, the 777, and he helped, and the theory came from math. By the way, he was a mathematician by training, and so he worked out that theory. And the problem is that his former professors at MIT didn't like it, and he was ostracized in the sense that they completely refused to even consider it as being a viable option for control theory. But it emerged that in fact it was all of the airplanes that were put together back then. They wouldn't have worked with the traditional control theory. They all adopted John's H infinity. And why is that? Because they knew that they could count on it, whereas they couldn't count on the traditional control theory. And that happens over and over again.
Interesting. Yeah, this is the problem the nuclear power industry has. They're not allowed to experiment and go through the trial and error phases because the regulatory state says 0 errors.
Yeah, so have you noticed how well SpaceX is doing in terms of the market now for boosters?
Yeah.
They figured out how to use them. And the way that they did it was completely different. Like you say, the traditional approach, going way back to the Saturn V, was that we got to get it working the first time, which means you have to have quadruple redundancy on everything and so forth. It worked. I mean, it was an unbelievably impressive feat of engineering, and it actually took us to the moon. So that was amazing. That's not how SpaceX did it. What they did is they sent up one after the next, and they would blow up. And they would blow up for different reasons. And the idea is that the first one you figured out, it blew up because the fuel was splashing back and forth, right? And so, you have to damp that down. Okay, so the next thing would present itself. But you could go through that whole process in a year. You don't have, or a couple of years. You don't have to spend 10 years designing and then making everything perfect. Now they're doing the same thing with their what do they call it now? Spaceship.
Starship. Yeah.
Starship. The Starship.
Yeah.
That's right. Which is a spaceship, but it is bigger than the Saturn V. And
I know, it's astonishing. Yeah, Elon's done a lot. Well, by contrast, the automobile industry was allowed to go trial and error, and we do tolerate still 40,000 people die a year on the highways just to keep experimenting. And where I was writing about this the other day, where's my flying cars from the 1950s, right? Well, we don't have those, but you got rack and pinion steering and seatbelts and airbags and anti-lock brakes and nav systems and stereo systems and anti-shatter glass and better bumpers, composite materials that make the cars lighter and more aerodynamic. 1,000 things, right? I like Kevin Kelly's principle of protopia. Just make the next one 1% better. And do that every year for a century,
Right.
and you'll have
But by
amazing.
the way, that is the way everything in science works. Everything in engineering works is that by its incremental advances. Now, that's normal. What Kuhn called normal science or normal engineering, where the first laser, for example, took a whole room of optics, and it was millions of dollars designing it. But now we have laser pointers, right? That was 50 years of optimization and miniaturization and commercialization and scaling up. But there are moments in time when there really is a real sudden shift where a jump, and we've lived through one, right? We are living through one. It's not a moment in time. It's really a generation it's our generation that saw this real jump in AI, right? From something that didn't work more, or it worked very, very traditional AI based on logic and rule-based symbolic processing. There were some problems for which that was the right solution, but the classic problems in AI, they didn't even come close, like computer vision.
So where are you pinning that start with Turing's imitation game and machines in the World War II?
No. This starts in '56 with AI at Dartmouth, the summer conference. No, it was very ambitious. They thought the computers seemed to be running rings around humans in terms of math, and just doing simple adding and subtracting and so forth, and speed. And then they would write programs that could solve games, or proof theorems and so forth. And they say, wow, look, if we can write a program that could do prove a theorem, which is one of the highest forms of cognitive achievement in humans, right? Proving mathematical theorems, right? Then wow, something like vision should be trivial, right? We open our eyes, we see how difficult could that be, right? Let's write a program. 50 years later, 10, $20 billion later, the DARPA would be pouring money, shoveling money down, into AI labs. And I'll tell you, they were not making progress. It was very, very slow progress, very slow progress. And it was because the computer programs are growing exponentially, right? Based on logic, based on writing logical programs. And it wasn't until learning was introduced. That was the real key turning point. And people say, well, neural networks, but the part of neural networks that really made the difference was learning from data, collecting lots and lots of data, and then having very large networks with many parameters, and using learning in order to tweak the parameters in order to be able to learn from the training set. And then the surprise and the real reason that they're used now and have been so successful is that they can generalize from a relatively small number of examples. But by relatively, I mean still a lot, but it's not like it's infinite. But from that, you can problems that were intractable before. And my favorite is language translation. Right? Do you remember? This goes way back to Star Trek. Remember Star Trek?
Yes. The universal translator.
Language translator, right? You remember that? That was science fiction back in the '60s.
You could understand Klingon.
That's right. It could translate alien languages, and why not? Now, of course. Well, now, okay, I have the equivalent of a universal language translator right here.
Yeah, they're pretty good. Yeah, they're pretty good now. Yeah.
It's gotten much better, much better. I mean, it's phenomenal. In fact, ChatGPT. GPT-4. Have you tried it? It's unbelievable.
It is unbelievable. Yes.
So here's what I did. I translated as a famous example of a failure of translation in the old days, and it's I think it's from the Bible. A little. That's right. It's a Bible that the spirit is willing, but the flesh is weak. Okay. So they translated to Russian, they translated that back to English, and it came out, the wine is good, but the meat is rotten.
Really?
Yeah.
That's hilarious.
Well, the words are ambiguous.
Yes.
And if you don't know the context, you're in trouble.
Right.
But now I did that. I gave this to ChatGPT before, and it translated it to Russian. Then I said, translate that to Chinese, and Chinese back to English. It was perfect. I was just shocked because, you expect a few substitutions, and
is that because the database from which it operates is so much bigger than it used to be? I mean, just orders of magnitude.
Of course,
yeah.
There's huge databases, but you can give it sentences that were never ever in the database, that were never spoken before by anybody, and it will do a really good job on it.
Yeah,
and it's it clearly is I think a real quantum leap in our what we can do now, what we're beginning to do. And by the way, okay, this is something that, so I was in China, and for my first book, which was on deep learning, the deep learning revolution. So I was in China, and it was early days. We're talking 2017, and so one of the questions,
early days, long time ago, way back in 2017,
dark ages. No, and one of the questions was, how can we be sure that this isn't just hype? Like it's always been an AI, right? Could this just be all hype? And how could I respond to that? Because it is hype. There's hype about everything new. No, here's what I realize is that, okay, we are now using deep learning to solve scientific problems that are so difficult that nobody was ever able to even approach it. And I gave a couple of examples, like protein folding. I said, look, physicists are hard-nosed, right? And they're not going to put up with hype. And unless it really works, it really works. Scientists are using it to make fantastic progress. The latest, by the way, is they've figured out they've trained up a deep learning network on a lot of simulations of weather, from first principles. And now they're able to, the New York Times had an article just a couple days ago of this, they can now produce weather predictions for hurricanes that are much more accurate than the supercomputers, and take just a small fraction. Instead of taking a day, it would just take a few hours on a home computer. This is like the weather. It's just like the universal language translator. I mean, that was one of the holy grails. I mean, how could that be? Well, it turns out that they're universal function approximators, and so weather is a product of some very complicated function, and so it can approximate it really well.
So, the old joke back in the 90s, we did an issue of this in Skeptic, when will computers achieve human level intelligence? And, the joke was, well, we're 5 years away and always will be. Maybe we're there.
You stole that from Fusion when I was a graduate student.
It was Fusion? Okay.
It was always 5 years away. And of course, that was the budget cycle.
Right. Yeah. By the way, did you know Paul McCready, the engineer?
Yes, I met him. Yeah, he was wonderful. Yeah.
Well, I bring this up because I knew Paul through when I was bike racing, and I knew him through the International Human Powered Vehicle Association, because he was designing aerodynamic shells to go around bicycles to make them more efficient.
Oh, yes,
and then there was this, they would have bike races with these shells on there, way faster than a regular bike and so on. Anyway, he's the one who connected me to the whole skeptics movement, because he was personally interested in that. And there was a lecture series at Caltech. I met the amazing Randy there, and that's how I got into doing all this stuff. But, Paul famously started Aero Environment in Pasadena from the money he won through the Kramer Prize. The Kramer Prize was the British industrialist named Kramer put up, I don't know, it was like $100,000, which in the 70s was a huge amount. And it was for the first human-powered airplane to cross the English Channel.
Oh,
there were two of them. You had to do a figure eight over land, and then you had to cross the English Channel. And Paul won both of those. They were each like $100,000.
Wow.
And he did it because, and people had tried and failed. He succeeded because, one, he was a glider pilot himself, and he knew how gliders were made, super lightweight with gigantic wings.
Right.
And he was also interested in evolutionary theory and biology, and he studied the fossil record. And, how did birds figure out how to do this? Well, evolution had, hundreds of millions of years of trial and error to create these aerodynamic wings. And the bird bones are hollow and super lightweight, and the wings are big, so on. And if you don't have massive wings and you have like a hummingbird, they got to flap really, really fast, or like a fly, right? So he designed and he did this at the timing when there were these like cellophane type material to go over these aluminum hollow tube structures that made the wing up. So basically he was saying, I used nature to win this prize. I just copied what nature spent 200 million years trying.
Wonderful. That's wonderful. So that reminds me of a taunt that was used against us back in the 80s, working on neural networks. Jeff Hinton, me, a handful of people. Jan LeCun was there. And the people at MIT and Stanford and Carnegie Mellon, well, they were the ones who were getting all the resources and the faculty positions and so forth. We were just young kids starting our careers. And here's how they convinced themselves and also kind of made fun of us and said, oh yeah, suppose you wanted to build a flying machine. Okay. And what are you going to learn from a bird, right? Because the bird flaps its wings, and by taking apart a feather and seeing what's in the feather, the composition, how's that going to help you build a big metal flying machine, right? Okay, so that was kind of self-evident for them, and so when I read the biography of the Wright brothers, I think it was, it came out about 10 years ago. So first of all, the Wright brothers spent a lot of time trying to understand how birds are able to glide with almost no energy, right? Well, that's because they had airfoils. Their wings were fixed, they weren't flapping, and they were able to glide for long, long distances. So what they did was they built a wind tunnel to test out different airfoils, right, at different velocities and so forth. And so this is how they got their idea from nature, just in the same way that Paul McCready did. And then exactly the insight that you showed, which was that you don't want to build things from metal, which is heavy. You want to build it from lightweight materials, which is spars, very lightweight wood, and then you cover it with canvas, right, which is the best technology at the time. That was like over 100 years ago. And, and then, okay, so you have to test it, right? And so you have to, get it off. They have motors are very, very primitive back then. You got to get off the ground and you're going to crash. And so, you can't survive a lot of crashes. So what you do is they went to Kitty Hawk, where there's a constant 20-mile-an-hour breeze on the beach. And then they would fly into the air so that the ground speed was very low. So when they crashed, it was just, 5-10 miles an hour, right? They survived. And then you go and fix the airplane, and then you figure out what to do next and so forth. And so the only thing they didn't get right, or at least they hadn't been as successful, was how to control the airplane. So they saw birds would move their wings like this, rotate the wings. And they tried doing that with the wood, and it kind of worked. But obviously the flaps were a much better solution, and they came later. But, they got off the ground way before the military did. The military were building these airplanes that were crashing and burning, and the test pilots finally said, no, I'm not going to go back into that can again. That's the end.
Yeah.
But here's the thing. Here's the thing is that although, we were mocked back then, well, look what's happened since then, right? Well, our intuition was dead on, that nature has solved these problems. So if you want to, the only existence proof you could solve vision was the fact that we see, right? And so therefore, let's take a look and see, crack the hood, see what's in there, and how is it doing it? And that's what Jan LeCun did. He was inspired by the work that had been done by Hubel and Wiesel on the visual cortex, and the structure in terms of the convolutions. Things like the complex cells, which were seen by Hubel as simple filters, and the complex cells that group together the information across space, and then normalization and layers and so forth. That all came right from the primate brain, and that's how, again, I mean, you learn from observing. You learn from that the trial and error. And by the way, Jan, he worked on this for like 20 years, right? LUDNet, he called it. And he would submit his papers to CVPR, which is the biggest computer vision meeting, computer vision pattern recognition meeting, and he'd get rejected. And he get rejected because they have these benchmarks that were designed for a particular kind of algorithm, and recognizing objects of a certain type. And his small networks at the time just weren't powerful enough. They didn't have enough layers. They didn't have units because they're very computation intensive. You need a lot of data. He didn't have it back then. Okay, so eventually, in 2012, Jeff Hinton and his two graduate students, Alex Krichevsky and Ilya Sutskever. You probably recognize Ilya's name because he's the guy in OpenAI that got into a lot of trouble, right, with Sam Altman. The board of trustees basically fired him. And in any case, in 2012, they used a GPU for the first time, and they used the ImageNet dataset, which is like 20 million images of 20,000 different categories, a really big dataset. Fei-Fei Li at Stanford put this together. She was a graduate student with Pietro Prona at Caltech, and I guess that was the first thing that she worked on when she got her own job. But, and it reduced the error literally in one go by 20%, and the benchmark at CVPR would go down by 0.5% a year, or maybe 1%. So you're just like 20 years into the future, 20 years of enormous number of graduate students writing programs for specific objects, the features that were distinguishable from making them distinguishable from other objects. And the worry about the pose, size, rotation is a very difficult problem. But learning, with the right kind of architecture, it turns out, if you use the right, it's called inductive bias, which is you don't do it completely randomly. You build the structure from parts that already are predisposed to be able to match the problem that you're working on. And convolutional neural networks are inspired by the retina, how the retina extracted features, and then that was passed up layer by layer.
Nice.
But the point I'm making is that the intuition about what's a difficult problem, you cannot trust your own intuition, because there's no reason why the brain or nature should give us any insight into that, right? It would just confuse us.
So let's think about or talk about words like thinking and intelligence. We have an intuition of what we're doing when we're thinking, or we know somebody who's intelligent. And is that the right metaphor or analog to what computers are doing? Let me set this up. When Deep Blue beats Garry Kasparov, I still don't think of Deep Blue, the machine, as playing chess in the same way that Garry Kasparov does. It just has more computing power, but it's not thinking through strategically like a chess player does. Maybe I'm wrong. Or my other favorite example, when Watson beats the great Ken Jennings, the greatest Jeopardy player of all time. Is it doing the same thing that Ken Jennings is doing? Not to mention, was Watson happy that he beat the great Ken Jennings, and he's now the Jeopardy champion? Of course not. Doesn't even know he's playing Jeopardy, right? So, what are the analogs there of thinking and intelligence between those examples and what we do?
Okay, so the really good question, and just to start with the Deep Blue and the chess, it was 90 something, 97, I think.
Yeah.
Okay, so first of all, the secret sauce there was building a special purpose chess machine that could go through moves much faster than any program on a general purpose machine, right? It was like a coprocessor. And what that means is that they could go deeper in terms of playing combinations. It's a combinatoric problem, right? If I do this, you could do all these other things, and therefore each one of the branching tree, I've got to go down those trees, and it's because it's like 11 ply for every for 11 possibilities for every ply, that means that it's going up exponentially. Okay, so but because the computer could do that much faster than humans, they were able to go farther and deeper, and that was a large part of was why they were doing. But it's interesting because they used a special purpose computer to do it. It wasn't a general purpose computer. Okay, now how does a human do it? Okay, so a human also has to do this search, but they don't search all possible combinations. They narrow it down from pattern recognition. In other words, they say, look, there's 2 or 3 at any given moment. There's 2 or 3 parts of the board and particular moves that they know from experience are going to be critically important, and so they take each one and then march it down and see where it leads. Okay, and then they pick the one that seems like it's the most promising. And but they still have to do the search, right? It's just that it's not as efficient. And what the computer didn't have, Deep Blue, was the ability to sort out and only search through the ones that had any hope at all, right? But but now here's the thing: the brain is a special purpose machine. It's not a general purpose computer. But what it does have, which is not in any of the computers that were used for AI, was ability to learn from experience and to recognize patterns and jump over the complexity of the combinatorial complexity. Just like I mentioned in chess, you could do the same thing. Is now being applied to so many problems. We talked about speech, language translation, speech recognition. Every day there's an article in Nature about some new way that they have for being able to design new drugs. It's a huge pattern recognition problem. It's a search problem, but it can be attacked with by giving it some examples and then generalizing from the examples. So 2 things there. First, it's the brain. And I should say not the brain, because there's this many species. Little ants have brains too, right? And they survive. They're very successful, right? I mean, come on. I mean, let's give nature some credit here. What you can do with 100,000 neurons, right? The flies have 100,000 neurons, and they. So I'm gonna tell you a story, and this takes us back to the late '80s, and at this point, we had developed learning algorithms for multi-layered networks, and there was the Boltzmann machine with Jeff Hinton, and then later Dave Romelhart with Jeff did the backprop, which is still being used today, by the way, in deep learning networks. In any case, we showed that it was possible to train these deep learning networks with more than with at least one hidden layer, and we were solving some toy problems, and so we were making progress. And actually, I worked on a problem that was not a toy problem, which was text to speech, pronouncing English words, right? That was actually, for the time, it was actually very, very a real world problem that even a small network with just a few hundred units could solve. But okay, I was invited to give a distinguished lecture at MIT, and I was this young puppy, right? I was just getting my career started, so I said, "Wow, this is amazing." MIT AI Lab was really the place where it all started. Marvin Minsky's there. And now the person who invited me was the guy named Dertuzis. I don't know if you've ever come across him. He's the chair of the department, computer sciences there. And he had written books about how computers are going to change, the marketplace and people's lives and so forth. It was very early. The computers were very expensive back then, and PCs didn't exist, but yet I think, let's see, 89. No, I guess the PCs were just coming out. Okay. And in any case, I show up. We had a great discussion, and then we go up to. He said we have a tradition here for lunch because we're going to have a discussion between the distinguished speaker and the faculty and the students. And I said, great. Okay. And so, as with elevators going up, and just before the door opens, he said, and by the way, they hate what you do. I was being set up. I was like the sacrificial lamb here. I said, oh my God. And so gave me 10 minutes. They said, look, start the discussion. We'll give you 10 minutes. And then
then we'll interrupt you.
Then it's our turn, right? We're going to go after you. They didn't say that, but I knew it. I saw it coming. Okay. So I went and stood in front of the sandwiches. And by the way, the Susan says, oh my, we've never had so many people here for lunch before. It was like 3 tiers. The senior faculty, the junior faculty, and then the students in the rafters, it was very popular back then. It was a big deal. Okay. And by the way, the lecture was going to be about using the backprop to train a small network to play backgammon, right? So it was early days of that.
Wow.
Jerry Tesaro was worked on that with me. Okay, so and I said, what can I possibly say in 10 minutes? And then I saw something. There was a fly circling around the sandwiches. And so I said to everybody, do you see that fly? And I said, that fly has 100,000 neurons in it. And with those neurons, it can see, it can fly, and it could reproduce itself. Okay. You have a supercomputer downstairs, it's Cray 2. It costs you $100 million. It can't see, it can't fly, and it's never going to reproduce itself. What's wrong with this picture? Now, dead silence. And then finally, one of the senior faculty puts up their hand and said, well, that's because we haven't written the vision program yet. That well, I happen to know that there was a DARPA program called strategic computing. They put $100 million into writing a vision program that completely failed. Completely failed. When the generals that were there for the unveiling, the tank headed for the generals, right? Instead of going straight ahead. Okay. And I said, you're good luck. You've had a lot of resources here, but look, we know this problem could be solved with 100,000 neurons, right?
Yeah.
Come on. And then Jerry Sussman, who actually is a very smart guy, and he said, well, we have mathematics, we have theorems, we can prove, that any computable function can be computed on a Turing machine. And, a Turing machine has a tape, it's just like a memory, and it has a read and write, and so it may not be, this is proven. We have proofs. And so my response to him was, oh yeah, well, how long is it going to take? How much time are you going to need to be able to recognize an object? And oh, by the way, if it's a tiger, you better find out fast because you're going to get eaten. Because nature doesn't play around. You have to be able to come up with fast answers, maybe not perfect answers, but fast answers that are good enough to survive. And literally, that was, these are the two big guns, right? They just shot them both at me, and they didn't. And this is a question every student in my lab can answer. There's an answer to it. And finally, a student in the back puts up their hand and said, well, the difference is that the computer downstairs is a general purpose computer. You can program it to do many different things. But the fly is a special purpose computer. That's all it can do is solve those problems. I said, yes, that's exactly the right answer. And it's the reason why it makes sense to go in and work out the circuitry. And it doesn't help, if you went to a digital computer and started working out the circuitry, it wouldn't tell you how to solve any problem. Because it's the program, it's a software. But it turns out in a brain, the hardware is the software. And so the algorithm is actually embedded in the actual special purpose machinery. And that was the end of the discussion.
That was your 10 minutes. That's all you needed. That's really funny. When I was in college, I had a professor assigned a book, with a little colloquial seminar called "To Know a Fly" by Vincent Dethier.
Dethier, oh, I knew he was the thesis advisor of Gelprin, who is my mentor as a postdoc when I was at Princeton, Alan Gelprin.
It was so interesting. I had no idea how complicated and smart these flies are. Like he had one section on figuring out how a fly lands on a ceiling. It's flying along like this, right? Here's the ceiling, and then the next thing you know, it's upside down, stuck to the ceiling. How did it get up there? Did it do like a barrel roll? And it turns out no, it flies along, then it sticks its two legs up, and then does like that, and kind of flips upside down.
Oh, that's smart, because it uses momentum.
Yeah. So, I mean, but even just figuring that out it was just a beautiful book on how science works. Again, trial and error. We just try this and this and this and this, try to finally figure it out, much by accident. But okay, so let's think about general intelligence versus, specific subsets like on the IQ test or the GRE or SAT or whatever. Intelligence researchers talk about G, small letter G, general intelligence. And that people that score high generally in G are also pretty good at all the subsets on the IQ test, right? And then there's like the evolutionary psychologists have that. They used to call it the Swiss Army knife model of the brain. And then now it's like the app, you have you have all these apps on your phone, and it's the apps. Hang on, let me show my apps here. All the different apps. So your brain has, all these different apps. So how do you think about artificial intelligence, natural intelligence, the brain as a general processor information versus the subsets or sub kinds of intelligence good at specific things? And if that's kind of more how it works, the specific things, why having high G means those people are pretty good at all those different subsets. And also, by the way, they tend to be healthier and they're more athletic and, just pretty much everything.
Well, so I, this is a very complex issue, and I've written. That's what my first book was about. That, right? And I can't summarize it, but I can give a few examples. But more specifically, the survival depended on being able to solve problems quickly.
Yeah.
Right. And that's what's, and the other constraint is you have to do it with very little energy, right? 20 watts. That's how much power you're dissipating just to think. And half of it is just to keep the cells alive, right? Not to actually do any thinking, but just, even
Oxygen.
when you're comatose, right?
Yeah.
Okay. So what nature had to do was figure out, first of all, how to build a body. That's not trivial. In fact, it's probably more complex than the brain in terms of the mechanics and the complex ways that our muscles work and so forth. We're not a simple servo, right? We have articulated fingers and things. Okay. And robotics is much farther away from being able to do a real humanoid body the way that nature did it than I think the brain. I think the brain is a simpler problem. But given that you have this body that needs food and it does need to reproduce, right? You've got to build special purpose circuits. So that's the first thing. And those were there from the get-go. Back in the fly, in the earliest brains, that they all had to worry about things like salt balance, right? And about oxygen. All of those problems had to be solved first. And that's what took so much time, right? To get that done. And that's a lot of that's taken place. A lot of the circuitry is down in the hypothalamus, which is kind of the boiler room of the brain. But it's very like breathing. There's a whole section there on breathing and so forth. So those are all special purpose circuits. Again, special purpose, but for specific parts of the body. They control the heart and that sort of thing. Blood pressure. And now, under varying conditions, right? You need more blood flowing when you're running, right? So you have to speed the heart up, and it's very complex. It's not a simple control system. It's very, very sophisticated. Okay, but now you want to build on top of that. You want to be able to have more capabilities so that you can have a bigger environment to look for food, right? So what do? Well, okay, so we put in some very sophisticated sensory processing on top of this. And the first one they put in was olfaction. That's clearly very important for both things that are good for you to eat and things that you want to stay away from. And a lot of it we still have, although in humans it's actually a lot of it is atrophied because we don't use it as much as we use some of the other sensory systems like vision. Whereas rodents still, they have 2,000 different olfactory receptors. I think we're down to like 600. But that was a trade-off. You can't do everything. Okay, so that's great. So we can do that, and those are all what is called the three-layer cortex, archicortex, which is the first cortex, which is very associative. It was able to do associations between inputs and outputs, like the behaviorists actually believed. But that by itself isn't very sophisticated because the same odor can mean different things in different contexts, right? If you smell something sweet, it might be a flower, but it might be some pesticide. You don't want to eat it, the pesticide. Okay, the humans are smarter, but how do you do that? So what you do is you put another layer on top of all of that. Before the neocortex is about 200 million years old, mammals. But before that, there was this archicortex, which did the job. It did vision, it did olfaction, did everything. And it got by. It got, animals are many, but each one had a specific niche. They weren't generalists. But with the advent of the neocortex, it meant that it's like a very powerful memory that could generalize, a coprocessor. Because if you look at the cortex, it gets inputs from all the sensory systems. And in fact, in the prefrontal cortex, it gets inputs from all of the body organ. It has representation of the body in it, right? It's not just the outside world, right? And that's all now being able to represent on a much higher level the abstractions of the sensory input, and then relate those abstractions to the ability to solve problems. And it turns out that that the way it was solved is just very elegant, which is that you have a system underneath that could could sequence actions. You see, you could think of many things at the same time, but you can only do one thing at a time in your motor system. So you have to be able to figure out how to do a sequence of actions to get to some goal, right? And that's what the basal ganglia does, which is beneath the cortex, okay? Cortex on top now basically is able to come up with abstractions that allow us to then choose actions which are much more sophisticated to reach more abstract goals. And that evolved now into what we now know, which is a very powerful learning system, so that an individual human can become good at almost anything if you spend enough time at it. Now, not all humans will become equally good. Obviously, there are some people who have natural talents for things, like Olympics is going on. So there are some people who have just natural talent for acrobatics, or natural talent for archery, or all of these things, running and or basketball, right? So you have somebody who's 7'2", right? That's going to give them an advantage, in basketball. So, but within the people who play basketball now, the people who really put a lot of effort into it, and for example, who is this basketball player who's really good at 3-pointers? Steph.
Steph Curry.
Curry, right. So apparently he would just go there every day for hour after hour after hour. And the point is that, if you're outside that line, a 3-point line, just by practicing enough, you can refine it to the point where you could just nail it, right? And that just takes an enormous amount of devotion and effort, and it's not fun. At least probably not always fun. And that now you could do that. And now we do that. You got a college degree in what area?
Well, my first one was experimental psychology, and then history of science after that.
Oh, okay. Well, then you become an expert, right?
Sort
You
of.
read all the books.
Yeah.
You take the classes.
I'm still learning.
Well, we all still learn, but
Yeah.
the point
Yeah.
is, though, that you picked history of science and you didn't pick music.
Yeah.
Right?
Well, because I gravitate toward things I'm better at and away from things I'm not very good at. In early, just trying out a lot of things. Like, well, I'm not good at this. I'm not good at that. Mostly, I'm not good at. Most of us are not good at most things, right? So you
Touche. I agree with that. but I'll tell you. Okay, here's a counterexample. Barbara Oakley. Do you know who she is?
I do. Yeah.
Okay, so Barb and I put together a MOOC 10 years ago, 10th anniversary, learning how to learn. Now, she's an amazing woman, right? Because as she put it, she flunked her way out of math in high school, right? She was a language major. She majored in Russian, and so she actually went on Russian trawlers, right? Went to the army, and then got involved in the Russian trawler business. But then she decided, when she came back, she said, I really want to learn math. And so he taught herself math. And in the process of doing that, figured out how to be good at learning. There's general principles of learning. And she, by trial and error, figured out a lot of them on her own. And I bumped into her at a National Academy meeting, actually, and she was giving a talk, and I had dinner with her. And it turns out we had, at UCSD, a Science of Learning Center. It's a big $40 million 10-year project that the NSF funded for 6 centers. And we were trying to use machine learning and neuroscience to try to come up with better principles and better practices for helping students. We were scientists. We thought we could do that. And that's another story. But in any case, I invited her to give a talk. And she was a hit, amazing lecturer. And in the audience, who's in the audience? It's not just the academics, but we invited high school teachers and high school students, right? Education. This is the educational system. She was able to reach every group. She had us eating out of her hand, in terms of knowing how to put problems to us. Okay, I want everybody to think of, how would you approach this particular thing? And then she ask people and then find out, well, here's another way that you probably haven't thought of. Okay, so in any case, we decided to put together this MOOC, right? Now because of the fact that she taught herself how to do this, right? She understood something about education. And by the way, she became a professor of engineering at Oakland University in Michigan, right? Mm. So that she was, even though that was not her forte and that's not something that she hated math, she eventually overcame that and she became an engineering professor. Okay, but now this learning how to learn has become widely popular. We have more than 4 people who have taken it in 10 years in 200 countries, and it really is something that allowed us to jump over all the hurdles. The educational system is really screwed up because there are the gatekeepers at every single place, the boards of education, the principals, the unions, right? And so it's hard to get anything into the classroom, very hard, even if it works.
Yeah.
But with MOOCs, they're free.
Yeah.
Anybody can take them anywhere that has an internet connection. And I get fan mail every day. When's the last time you got fan mail, Michael?
Oh, I get emails every day, pretty much every day. Yeah, I got one this morning, but I don't have a MOOC. But I know what you're.
No, I'm pointing out that it's actually good to get positive feedback.
Oh, I know, it's great. All right, Terry, let me bring together several threads from what we've been talking about here. So a few years ago, we published an article in Skeptic by a guy named Louis Lederberg, who is a tracker, an animal tracker, and also a philosopher of science. So how about that for a combination? Anyway, his article was about how tracking animals is a form of reason and rationality. And that, in fact, science is not a new thing at all, that hunter-gatherers use hypothesis testing all the time. So you come across some tracks in the sand, and they can deduce from this, cloven hoof print, and it's leaning more on the one side than the other side. You can kind of tell roughly how big the animal is, and then maybe there's a big blotch in the sand where it laid down last night, and now that it's gone from this underneath this bush, now the sun's over here. There's some water over there, so we can deduce that it probably went that way, and we'll look for the tracks. So it's kind of a Bayesian hypothesis way of thinking, test and retest and keep getting new information and so on. His point was that, in fact, humans are naturally rational for the thing you were talking about there, solving problems. Okay, several threads here. And then I was thinking about Dawkins' selfish gene model, that everything we've just described about, that you just described about how the human body works and the brain has to run all these different programs and so on. Dawkins famously called us survival machines. The bodies are just survival machines built by genes who are just trying to get themselves in. They're not trying to do anything. They're just getting into the next generation, and the survival machine is how they do that. And what does that survival machine have to do? It has to solve problems, really basic problems, and then scale up from there. Okay. Last thing, you talked about these cathedrals with the big structural support system on the outside, or the vaulting arches that hold the ceiling.
The flying buttresses.
Flying buttresses. So here I was thinking about Steve Gould's idea of the spandrels of San Marcos, of the great cathedral. And that, in between the two arches is this space where they have all this beautiful artwork. But that's not why the spandrel, that's a spandrel. They're not there for any purpose other than it's a byproduct of the fact that you have these arches crossing each other. So he called those spandrels. So, why are we, so last thread, Alfred Russel Wallace famously broke from Darwin, in which he argued, for survival purposes only, you really only need a brain about the size of a chimp or so. Humans would be just fine. Solving problems, everything you just described. Why do we have music appreciation and aesthetic appreciation, higher mathematics, and so on? And you can just carry it on. What's the purpose of solving problems like quadratic equations or quantum physics or anything like that? Why are we able to do that, generalizing from these very specific problem-solving neural networks or whatever? That is, I guess what I'm asking is, to what at some point thinking and intelligence goes from this obvious problem solving for evolutionary purposes to this higher stuff. Like, why that? Is that just a spandrel?
Very, very intriguing question that many people have thought about, and you'll find books written about it. In fact, we have a institute. It's here at UCSD, which is devoted to. It's called the anthropogeny, the study of the origin of humans. How did we get here?
Yeah,
and it's been. I've gone to a lot of their lectures, and it's fascinating. Just how evidence is coming from everywhere. From looking at the genes in Neanderthals and coming up from understanding something about civilizations rising and falling and so forth. Okay, so. And I'm not an expert on this. I just, I follow things. But here's something I've just noticed. I mean, this is an analogy with now with AI, right? It's always useful to have something concrete to point to. One of the things that we didn't realize back in the 80s was, how would this thing scale? In other words, as you build these networks bigger and bigger, would their performance get better and better? And would it poop out just like almost all AI algorithms with combinatoric explosions? They were not capable of getting solving these general problems, the general intelligence problems, and we didn't know. Because we didn't have enough computer power. We now have 1 million times more computer power and 1 million times more data. And here's what we've now experienced is that when you as you grew, I told you NetTalk was that tiny network that literally I have a tape in which you play a book and it would read it out loud. I mean, it was amazing. It was a tremendous demo. I mean, people were just stunned when I just gave talks like this. and the linguists will write these 300-page books with all the rules in them and exceptions to the rules and all the way down. But at some point, you start in 2012. We had enough computer power to crack the vision problem. Not to completely solve it, but I'm saying that reached the point where it was now reachable. And that happened over the next 10 years. Basically, it's now on ImageNet. Now they have the benchmark down to the point where it's like 1% error, 0.5% error. I mean, it's truly amazing now what's capable. And what's been happening is that as you ratchet up in size in terms of the number of units and the number of connections and parameters, you reach these thresholds where you can now solve problems that you couldn't solve before, right? It's like a phase transition. Now suddenly, and the latest one was in November 22 was when OpenAI released ChatGPT to the public.
Yeah.
Now, it has all kinds of problems, but it's still stunning about what it's capable of. It talks to us. It's not completely reliable, but the steam engine blew up, so we have a precedent. But here's the thing: is that one of that they didn't realize that there were problems it could solve that nobody even built into it or imagined it could solve. A lot of natural language problems, computer programming, right? I mean, these are things that once you have the ability to abstract at a high level with any database, it opens up many other problems that before you couldn't even touch or you couldn't even imagine. You couldn't get there, right? And so maybe that's what happened over evolution is that, and there's a lot of evidence that in the case of humans, language emerged in order for us to be able to hunt. And take down animals that were much bigger than us, right? The mammoths. Because we can organize just the way you described. That we can work together and look at the experience that we've had in different strategies and so forth. And language basically helps you coordinate a large group, and not necessarily large, but maybe a dozen hunters who are going to work together to corner the animals and figure out how to get them into a chute where then you could spear them, right? I mean, it's a typical human tendency, right, to try to trick others to doing what you want them to do. And that's what language is really good at.
Yeah. Is it your sense, since you've been working on this for a long time, that this now is different, that we've made this is a phase transition, these large language models, ChatGPT, whatever edition is going to be, that's it. We're on the verge, and we're past the 5 years and always will be. Now this really is probably something big.
It's I think it's just a passing. I'm not even sure if it's passing, but it is a level, and there's a whole sequence of these levels that once you can't even approach a difficult problem until you have enough representational capacity to take it in and enough data, I should also say, to be able to do that. By the way, it turns out the world is a wonderful source of data. Just looking around and picking things up turns out to be a fantastic way to train up brains. And that's clearly how babies learn about the world, through trial and error.
Right. They're little experimentalists they're little scientists. Right. Alison Gopnik talks about that. So, and would this be the distinction between artificial intelligence and artificial general intelligence, AGI?
So what is artificial general intelligence? Okay. Again, nobody really has, as far as I know, come up with a really solid definition. And in fact, here's what's happened. I mean, this is the history of AI, is that, okay, here's the problem. Language translation, that's intelligence. That takes intelligence. Oh, we've solved that problem. Well, maybe that's not really intelligence, right? Maybe that's just some automatic system, right? This is a more difficult problem. And that's where I think AGI is. AGI, so here's the real problem, is that we actually don't know what the mathematical problem is that our brains are solving, right? When people in computer vision, their definition of solving it was to create an internal model that is veridical, it gives you exact coordinates of everything that's out there in 3D, so that you can now pass the coordinates to the motor system so you can reach out. That was, we don't. It turns out we don't. That's not the computation the brain is doing. We have our eyes zipping around and picking up pieces of data and putting them together, integrating them in some abstract representation up here. And so we don't really know how intelligence is really handled in the brain. And all the intuitions we've had, the introspection is very unreliable. I would not rely at all on anything that someone was a problem they're trying to solve, that they thought that the brain solved. I think the nature is solving different classes of problems that are successful, obviously, but are solving different problems that maybe are more solvable. We may never be able to write a computer program that fulfills what people in computer vision want it to do, and maybe you don't need to, right? I think we get by perfectly well with our ability to reconstruct pieces of the world. The beauty of the world is always going to be there. We don't have to basically why reconstruct it if you just go in and query. You could sample it whenever you want.
Yeah. Well, let's just take a specific problem like self-driving cars. And you're scaling up from very specific things like lane change or staying in the lane or your speed control, cruise control. That was a big step with my Tesla, and now my Ford Explorer also has this where it can tell how far the car is in front and slow down and go faster and so on. That was a huge game changer. But still, compared to complete self-driving, those are pretty simple. Is it that the problem is that what if there's something new on the highway? So you program into it where every stop sign is, but what if the stop sign gets changed to a yield sign, or they put up a traffic circle? Now there's no more stop sign. And does my car then depend on the people at Tesla programming it and sending out, over the internet that there's now a traffic circle there and not a stop sign, and now it knows it? Okay, or is that in the cameras and in the computer in my car itself, it realizes, oh, I see, that's something different. Or if a rock falls down or a tree goes across my little road, is it going to know that?
Well, yeah, that's one way to solve the problem is if you just accumulate enough of these edge cases, you'll eventually run out of them. But you'll always have something that never happened before, right?
Yeah.
No, but so first of all, you have to understand that humans who have learned how to drive basically are doing a completely automatic pilot themselves. Yeah. They're not thinking.
No.
They don't have to. They maybe at the beginning they kind of thought themselves, am I too close? Am I too there? No, your visual system knows how to calibrate things, and then off you go. Maybe with a new car, it takes a while to adjust yourself and so forth. But that's the basal ganglia. The basal ganglia takes over and will keep you going unless you get to a situation where things are a little bit tricky. And I've noticed this myself. When I come to an intersection and there's other cars and people, I really do have to start thinking. I have to say, well, where are they going and who's first? So when you reach a point where it's not there isn't a pre-learned sequence to solve the problem, you shoot it up to your cognitive system. The cognitive system now is very slow, but it's more flexible. It's able to consider more than one possibility, and it can simulate things. It can simulate what would happen if I did this or I did that, and so forth. But it's incredibly slow, and it's not particularly accurate. But at least it gives you it's a hypothesis generating system, right? It generates new hypotheses for what's going on out there, and that's what's not in the self-driving cars yet. Mm. But maybe the next generation of these deep learning networks will reach a level of abstraction where on top of what they're doing now, which is recognizing objects, and then be able to recognize situations, scenes, that are seen, and how then to become flexible in terms of interpreting what's going on, coming up with hypotheses, testing them, and so forth. Just the way you described little children that are growing up, right? Yeah. They do this all the time.
It'll be interesting back to where we were talking about, zero tolerance for errors. One of Elon's points is that, 40,000 people die every year in the United States in automobile accidents. What if I can reduce it to 20,000 or 10,000 or 1,000? Would the regulatory state allow 1,000 people a year to die because of self-driving cars?
Well, this is a psychological problem, and it's the same thing. Airplanes are by and large an incredibly safe
Yeah.
mode of transportation. And but when a plane goes down, once a year or less, there's a huge amount of publicity and so forth, and people say, "Oh, this," but they don't realize that it's like 100 times safer than taking an airplane, driving a car, right? For
Yeah.
the same reason you gave. But psychologically, for some reason, we tend to emphasize the ones that stick out. Now, the real problem, by the way, in my 2017 book, Deep Learning Revolution, I realized that the real problems were not going to be the keeping on the highway, right? The real problems are going to be these edge cases, but also regulatory problems, just the ones that you've brought up, which is, will they allow us to in fact, Tesla apparently had 1,000 accidents, that had been reported.
Yeah.
But of course, Tesla's argument is that, well, if we have tens of millions of miles, and that's 1 out of 10 million or something, 1 out of a million is pretty good, right? That's not doing too badly compared to humans. The real problem is that there's going to be a transition period when there's going to be both humans driving and machines driving, and humans are very unpredictable about what they do, because if some of them are drunk, some of them make bad decisions, or they don't see you, right? I mean, that happens. That's why there are 40,000 accidents, right? But if we can get rid of all the humans, it'll be a lot easier.
Yes.
Now they can talk to each other. They'll talk to each other. They'll know exactly where they are, what they're going to do, and there's no road rage.
That's right. Well, hopefully, because what if the machines want something? Okay, let me get to that point. Okay, so thinking, intelligence, rationality, reason, these are tools for solving problems. The goals that an organism has, it comes from somewhere else, right? Just their emotion or intuition, or my instinct is to survive. That's my goal, and now reason is my way of getting that. So here's the alignment problem that everybody always talks about. What if you make this AI so smart, or AGI or whatever, that it's no longer aligned with our goals? It has different goals, and it's a lot smarter. Do you worry about that, or how do you think about that problem?
Well, there are humans that have different goals too.
yes. Vladimir Putin.
Exactly. Okay, but here, okay, again, this is a chapter in my book. By the way, I have a Substack out now called Brains and AI.
Oh, all right.
And by each of the topics that you have raised, all very interesting, are going to be
good.
In subsequent posts. I've taken notes here, so I know about some of the ones that that are particularly I want to work on, that are not in the book. That's the whole purpose. The book will be out in October, by the way.
Mm-hmm.
Okay, so here's how we train these networks. We have this a ton of data. We fed it in. We feed it in, one after the next, and then we update the weights. Just like a mad statistician who's just tweaking the weights to reduce the cost function, right? There's a cost function, which is the error, or it's sometimes called the loss function, but it basically is what you're optimizing. You're optimizing this function, and that's how you twiddle all the weights. Okay. At the very end, it's at the mercy of the data. If you put in bad data, you get bad output, and that's what a lot of the people have experienced, right? In terms of bias and hallucination and so forth. Okay, so, well, how do we raise children? We raise children by giving them feedback early on, before they become physicists, right?
Or drivers.
What's good and bad, and what's dangerous. And it's, by the way, that's reinforcement learning. Mm-hmm. We know that's the basal ganglia. We actually have an algorithm that can do that. And it was used, by the way, for training up AlphaGo, right? That could be the world champion, Go champion, okay? So, but the point is that you have to give it reinforcement about the culture that you're in, about the values of the culture. If you want it to be aligned with us, it has to know what to align itself with, right? It has to know that. You have to tell it explicitly. No. Don't use that word. That's a bad word. And by the way, children if you just think about it, they believe in crazy things. They have fantasy worlds that they believe in. They believe in Santa Claus, right? And they hallucinate. They hallucinate, right? Well, these large language models, they're basically growing up children. They hallucinate just like little kids, So we have to learn how to bring them up the same way we bring up our own children. And that's where the future is, to help solve a lot of those problems right now that are really important ones and issues that have to be aligned with now then the other problem is, okay, which culture do you align it with, right?
Well, presumably whoever the culture is of the programmers. But
we have wars.
Yeah, well,
cultures
that's right.
have wars. I mean, I'm not sure that's the best solution.
No, probably not. There's probably some political system that's going to get involved in all this regulatory state of the whole system. Okay, so the alignment problem example of the paperclip efficiency manufacturer, right? This is Bostrom's paperclip maximizer,
right.
And that it's so smart it can produce anything we want, but it's so dumb it doesn't realize that turning us into paperclips or whatever is a bad idea. I'm oversimplifing this, and
no, I know the story.
You know the story, right? So, what is your response to that's the alignment problem?
Okay, look, my good friend Jeff Hinton actually has come out with a concern about superintelligence, right?
Yeah.
And he has some really good points to make. He said, and it's not this paperclip business. I think that's a kind of a silly example, in a sense that silly not in a sense. It's actually it's a fun example, but it's not the real problem. The real problem, as Jeff points out, is that if it can program itself, right, you can lose track of where it's going to go. It can get way beyond where we are into the next level, right, if it had enough resources. And the other problem that he points out is that the real problem is that what if it gets in the hands of somebody who's bad,
yeah,
and uses it in an evil way, and that's happened with every weapon.
Yes, sure, Kim Jong-un.
Yes, and after all, we did bomb the Japanese, who atomic bombs, Hiroshima and Nagasaki. We're not proud of that, but it did stop the war. But that was a justification. But the reality is that we're, as a species, we're just not that reliable in terms of doing good all the time, right?
Yeah.
And in order to survive, we couldn't have. Because it's the tribe that is more clever that wins, right? That then passes the genes on, and that's how we got here, right?
But isn't it that we want things like, I want to conquer the world or whatever, or I want to control the resources of that country over there, so I'm going to invade. No AI is going to want anything. It doesn't have wants and needs and it's emotions, right?
Yeah, no, it's not. In fact, I mentioned earlier that we had to have a lot of inherent instinctive needs, for food and air and reproduction. Otherwise, we wouldn't be here, right? So there's some basics that needed to be put into us. But there's a lot of freedom once you get out. Once you solve those problems, there's a lot of dimensions and degrees of freedom now that can be put on top of that survival. But you still have there must be a loss function at a higher level in our brain that we use, like when we like music, right? We really love music. We love dancing. We love good food. We love, in other words, there's appreciation of fine art and ballet and beautiful science, right? I mean, we have that capability and there must have been once you have a loss function that is really good at coordinating the body, maybe what you do is you replicate that and now use that loss function over and over again in all these other domains, right? Getting better at something. appreciating something at a deeper level. And so I think that's how I think nature did it. I mean, maybe not exactly that way, but and evolved systems that then could be repurposed, from different to do different things that they weren't designed for originally in terms of the hobbies that people have. But I think though that we are just so we just humans are not very good at imagining the consequences of a technology and for example, you remember when the internet first became public back in the 90s?
Yeah.
Could you have imagined the impact it's going to have on every aspect of your life? No, they're not good at that. Not even the people who built it.
Right.
Could it foresee it? I mean, it's amazing. And so the same thing is happening now. We've built this new technology that can talk to us.
But is that reason then for concern about an existential threat of AI? Not the robot apocalypse, but more this, they don't even care about us. They don't even.
It's possible, but the reality is that it's just a machine. Is the internet okay? Did that lead to an apocalypse? Well, I guess you could argue, fake news,
social media, fake news,
social media, and so forth. Yeah. That's because it hasn't been regulated. We haven't figured out how to regulate it yet, and it's the same thing that's going to happen with AI. Once we've realized the unintended consequences, we'll figure out how to regulate it. Just as long as we have the off switch, right? We have to keep our hands on the off switch.
Yeah. I remember this when the LLMs were first released, and Eliezer Yudkowsky wrote that Time magazine op-ed in which he said, I'll just read it, and you can respond. Many researchers steeped in these issues, including myself, expect that the most likely result of building a superhumanly smart AI under anything remotely like the current circumstances is that literally everyone on Earth will die. Not as in maybe possibly some remote chance, but as in that is the obvious thing that would happen. If somebody builds a too smart AI under present conditions, I expect that every single member of the human species and all biological life on Earth dies shortly thereafter. And I've been trying to get a pathway of how this could possibly happen. The only thing I could think of is if it made like a super realistic looking video of the president of the United States saying, launch the nukes against the Russians. And then the Russians watch the video and go, oh my God, we better launch a counter attack or something.
That actually was a War Games. It's a very old.
Yeah, I know. Yeah.
Put it this way: everybody is entitled to their own opinions, but not to their own facts.
Okay.
Yes. And his opinions are based on very, very thin speculation. And great. I'm glad that people are speculating. In fact, I'm glad that some people are worried about the worst case scenario, right? I mean, let's just have someone who's smart think about that. That's good because, if it ever comes about, we'll have thought through what the issues are and have some plan, I hope. But I think that we can't even imagine what the real issues are going to be.
Yeah.
And that might be even worse or, more subtle. Like, for example, if they've solved all our problems for us, what's left for us? We may get bored, right? In other words, what happens to people who have, when they retire and they go play golf, right? It's just not the same thing as running a company, where you have a lot of power. You have no power over your putting. You're at the mercy of your motor system.
I like this quote from Kevin Kelly, co-founder of Wired magazine and one of the pioneers and all this stuff. Generally, what people thought, he said he was going through early issues of Wired, which he co-founded, decades after the fact, to see what everyone was predicting for the web. Generally, what people thought, including to some extent myself, was that it was going to be better TV, like TV 2.0. But of course, that missed the entire real revolution of the web, which was that most of the content would be generated by the people using it. The web was not better TV. It was the web. Now we think about the future of the web. We think it's going to be a better web. It's going to be Web 2.0, but that's not the case. It's going to be as different from the web as the web is from TV.
I like that. I think he's got it dead on. Where did you read that?
That was in his book. Was that What Technology Wants? Let me see what I put for a reference for that. No, let me see. I'll give you the reference for that. Number 15 is Oh, no, it's an interview he did. Let me see. Here it is. Oh, Edge. This was his conversation with John Brockman
Oh, good. Yeah.
called the Technium. Yeah, he called it the Technium, right. I think that was after What Technology Wants book. Yeah, I'll send you the quote.
Okay. Well, I'm also a John Brockman author, so I was in a lot of those Edge books.
Yeah.
But okay, so actually, it's a little irony here. I've always wondered about this. Maybe you have some insight. We're living in a wireless world. Why would they name a magazine Wired?
That's right. That is really funny. Oh my God. The new version should be wireless.
Wired 2, right?
Wired 2.0. We got even more wires than we had before. That is really funny. Yeah. So, okay, let's just hit a couple of big questions here because we're pushing over an hour and a half here now. What insights do you get from any of this about the nature of consciousness? Do you want to address the hard problem of consciousness on this?
So my colleague for many years, Francis Crick, when he shifted from molecular genetics, by the way, when he was young, his mother asked him, when you grow up, what do you want to do? And he said, there's two problems I want to solve. The first one is, what is life? And the second one is, what is consciousness?
Doesn't want to be an astronaut or a baseball player. Right.
So he solved the first, and then he went on to the second. And and he was very sensible. He said, well, first of all, you can't define it. So let's pick out something that you might be able, some aspect that you might be able to solve. And that he picked out visual awareness. That was a nice way because we knew more about the visual system than any other part of the cortex. So let's start there. And then Christoph Koch came, and then they had the neural correlates of consciousness, NCC. And again, they made some progress, and it actually was extremely confusing because they were looking for single neurons that were conscious, right? And that clearly is not how it works, right? The responses of single neurons that are correlated with your consciousness. Okay, so I think that it's probably wrong to try to answer that question head on with what we know. But I think that now that we have incredible tools and techniques now in neuroscience, we can record from tens of thousands of neurons simultaneously from dozens of parts of the brain. And what we're seeing is absolutely spectacular, something that nobody ever would have guessed in terms of how populations of neurons are organized and how their global patterns of activity of the brain emerge, especially when you're sleeping, of all things. And so that's got to be related in some way, in some place, somehow to the global, they call it the global workspace, where we have this kind of impression that we're able to integrate all that information that's coming in our senses, right? It's not coming in as separate channels and separate things. Somehow it gets into a global representation. And I think that once we've understood how that's done mathematically, and we're like I say, we're making a lot of progress in machine learning, for example. There are papers that are coming out that are analyzing how information flows through transformers, for example, in large language models. And then now we can analyze activity patterns in human brains, and it turns out that there's very similar flows of information. It turns out to be low dimensional, like 5-dimensional. I mean, everybody was thinking millions, billions, right, of neurons. It must be a very high dimensional problem. No, it's a 5-dimensional problem, but it's different 5 dimensions for every problem. So now we have to figure out how you integrate together all of those low dimensional solutions. So I think we'll eventually reach that point where we have a mathematical explanation for how the information is both represented and is processed and then used to decide about actions, and also how you decide what information to store long term. And I guess that's about as far as I've gotten.
Well, it may just be a conceptual problem in which we've not conceived of it the right way to answer it in the way that scientists like you would like to
Yeah, that
be able
I
to
would put
do,
it that
because
way.
it's
I know.
often defined as what it's like to be something and what it's like to be a bat or whatever.
Yeah, they go.
Is that
Okay,
really the right way to do it?
Francis once gave me some advice about philosophers. Right? He said,
Don't listen to him.
no, no.
Oh.
Francis said, listen to their questions, but not their answers.
Oh, okay. That's funny. Yeah, yeah. Well, but so here, from what we've been talking about, is it that at some point there's a phase transition where the complexity of the system gets such that there's an emergent property of something new that comes out, like consciousness or free will or being aware that you're aware, and maybe we call that sentience. Maybe that's how it happened in human brains. There's a scale up, like Dennett talks about, degrees of freedom, degrees of sentience.
Possibly, no bets on any of these possibilities right now. But one thing that we should, okay, here, let's, we're living in animals in the world, communities of animals that have their own form of awareness and ability to think about their particular niche that they're in, the problems they're trying to solve. Right? There's no doubt about that. Right? They wouldn't have survived if they weren't good at that. Their brain wasn't good, and their brains are very similar to ours. It's not like our brain has some kind of language organ or a coprocessor. It's basically the same. With 98.5% of all our genes are the same as a chimp's, right? So it's got to be just twiddling some of the endpoints there, and it's not like we have some special consciousness processor.
Yeah. Well, I mean, I guess that's sort of the big question of the singularity is near, and now it's near.
No. That's the problem. There is the
the
there's not singularity. No. We've already gone through many singularities in technological singularities, cultural singularities, and there's going to be a whole road ahead of us of singularities. It's not the end of the road.
Okay, interesting. Because Ray is on the road promoting his latest book, in which he's putting the date at 2045. The big thing is going to happen. What you're saying is it's already happening. It just incrementally.
It's a process. And it's incremental, and then it suddenly is a jump, and then it's incremental. I told you that, right? This is the way it works in science. The way it works in culture. Yeah. It's always like that. But but we can't predict them. That's the problem. We just can't predict what the consequences are and when it'll happen.
Yeah.
Very, very interesting that we're living in interesting times right now, because they're happening faster. Things are happening faster than they did in the past. So maybe that's really what's going on. Things are accelerated. Yeah.
Well, to me, just a final point here, just so much of that singularity talk and much of this becomes sort of science fiction, and then almost like religion. Like we are living in the most special time in human history, in which we're the first generation that will live forever and see super omniscient type intelligence will become gods. And I just feel like, hang on, I'm not back in church here, am I?
Listen, there have been many individuals who have made, predictions about the second coming. And the date comes and goes, and that's it. It never. That's a fool's game to put a date on something, because you're guaranteed to pass the date.
Yes.
Bye.
Right. So, well, let's just hope you and I make it to 2045. I'd be happy just to make it there. These people that tell me, don't you want to live to be like 1,000 years old? I say, look, just get me to 90 without Alzheimer's. Can you do that? Well, no, we can't do that yet. Okay.
There you go. No, that's really the issue is not how old you are, but how the quality of the life that you have, at whatever age you are at, and
that depends on solving very specific problems, like fix my knee. Right.
Well, that we're gradually working way through the body, but so far no one has figured out how to do a brain transplant.
Right. Exactly. All right, Terry. Thanks so much. Thank you for your book. Here it is again: ChatGPT and the Future of AI.
Great. Okay, Michael.